Science at the University of Maine at Augusta, and today we're going to be looking at, very briefly, the basics of social networks. Why study social media as a social network? Well, what could be simpler as a way of understanding social media, a really big phenomenon? Let's boil it down and let's say we can understand social media as a combination of just nodes, usually represented as a circle, and edges, the lines that occur between circles. It gets a little bit more complicated, but not much more complicated than that. What could be more accurate than to describe social media as a social network? After all, social media is all about building and maintaining relations, and most of social science is all about individuals. And what individuals do and individuals think. Social media is about the connections between them, and social networks are about the connections between those individuals and what those individuals share. So the third reason is what could be more different. If you're considering going into the field of social media as an analyst or as a marketer, as a designer, know that 4 out of 5 social media analysts don't know about social network analysis or how to use it. 99 out of 100 social media producers don't know about social network analysis and how to use it. That means you should. It's a great tool. It's a leg up. It'll differentiate you from everyone else. So the elements of a network are very simple. And you're going to find that there are a lot of synonyms for terms. One synonym for a network is a graph. A synonym for a node is a vertex. A synonym for an edge is a tie or a link, a connection, a channel. Okay? These are the elements of a network. That's it. Everything else is elaboration. So we would identify A as a node, B as a node, C as a node, and D as a node. And we would identify the lines between them as representing connections. Now, in this network, there are all kinds of possibilities about what it could be. What could the node be? What could the edge represent? The list is almost endless. For instance, we might think of people, and that's usually where we start with networks. A could be Al, B could be Ben, C could be Cleo, and D could be Dot, and maybe friendships are what describes those lines between them. So we would say here that Al and Ben are friends, that Al, Ben, and Cleo kind of make a circle of friends. They're all friends with one another. Ben is friends with Dot, but Dot is not friends with Al and Cleo. So often the pattern of the lack of ties is just as important as the pattern of where the ties are. We could also think about it as a set of corporations. Here are 4 prominent corporations. One's a bank, one's a technology firm. Maybe they purchase and trade things between one another. And those lines are about trading or purchasing relationships. It could be. These could be social media accounts. And they could be Twitter accounts that have shared information in the last month. It could represent that as well. It's the same structure. It's different content and different objects occupying them. Sometimes corporations, sometimes social media accounts, sometimes people. And the 3 are not necessarily the same. Now, you'll notice before this picture that you're looking at here, there were no arrows. When there's no arrow, there's no direction. This is usually representing the kind of tie that wouldn't have direction. For instance, in Facebook, 2 accounts can be friends. It's not possible for one account to be a friend of another, but for that friendship not to be returned, it has to be returned. That's the way that Facebook is built. If you're friends, it goes both ways. But in Twitter, it's possible for individuals to follow others. but for the following not to be returned. So A could follow B, but maybe B doesn't follow A. So in this case, the tie has a direction, and the direction that a tie takes is shown with an arrowhead. Some nodes are alone. These can be called singletons, E, or isolates, individuals who are separated from the rest of the network and don't communicate with any others. We can look above a single node or a single tie or a single edge or a single vertex, to use synonyms, to think about dyads, triads, and other structures that come out of bigger features of a network. Now, in a dyad, you could say that it's an untied dyad, or you could draw a line between them, an edge, and all of a sudden now it's a tied dyad. In a triad, a trio of vertices, there could be no ties, there could be one tie, there could be two ties, there could be three ties. If we're working with an undirected network, a network without direction, then that's all the ties you could stuff in there. If we're working with a network with direction, then you could say, aha, I have three ties, but you could fit three more in. You could have a double-headed arrow. That's four ties now. Double-headed arrow there, which means that it's a directed relation that goes both ways, and that's five. And you could fit another one in there, a sixth tie. So what's interesting, and I hope you just noticed, is that the circumstance of everybody being tied with one another gets more complicated the larger the number of nodes that you have. So it's very easy with the dyad. It's relatively easy with the triad. A situation in which all possible ties are present with four nodes, I have to start drawing a little bit more. What have I just drawn? I've just drawn a set of cliques, also called cliques, depending on how you pronounce it. A situation in which, for a network, all possible ties are present. For these three networks, a dyad, a triad, and a quad network, this is what all possible ties being present would look like. Notice the numbers here. Between A and B, a dyad is just one possible tie, or two possible ties if you have direction. For a triad, there are three possible ties, or six if you include direction. For four nodes, there are 1, 2, 3, 4, 5, 6 possible ties, or 12 if you include directional ties. This goes up very quickly as the size of your network goes up. And in fact, there's a formula for it which we'll consider in another class. Finally, we can think about not just the number of nodes, but the kind of path that is created by connections between the nodes. And a path is also sometimes referred to as a walk. Imagine that you are standing on a node and then you try to get to another node, and imagine that you can only travel by a tie or an edge. So in this case, the path length is the number of intervening ties or edges between these nodes or vertices. So we would say from A to F is 1, A to E is 2. The distance between A and E is 2. What about A to E? Oh, there's another E. Pardon, I made a mistake here. What about if we go to G? That would be to 3. Okay. And then what if we say this is H, I, J, K? Always check your work. Okay, 1, 2, 3, 4, 5, 6, 7. That is a path length of 7. Here we can think about path with direction. Let's take a look at the example of A and E. Okay, we have ties with arrows. And what does that mean? If we have an arrow going from E to A, that means if we're trying to go on a walk, you can only go one way. So you can go from E to A, but not A to E. So the path length from E to A is 1, but the path length from A to E is 1, A to F, 2, F to G, 3, A to E. Okay, so if we have direction, then the distance between two nodes can be different depending on which node you start from. I also want you to notice that in this case, there are some infinite distances. If this is Hij here, node K, this is node I, okay, this is node H, maybe this is node J, GHIJ as a set of nodes can't be reached from A, B, E, F, or G. We say that that path length is infinite. It's huge. There's no length that will get you from one set of nodes to another. And when that is the case, and we have two sets of nodes that are separated completely, we say that each of those sets of nodes is a connected component. Components are sets of nodes that are separated from one another.